Hello Internet. In this video, we are going to learn how gradient descent works. We are going to start by using Tinygrad to do gradient descent. And then we are going to implement it from scratch using just Python. So make sure that you watch till the end. First, we need to accept that a derivative is another name for a gradient. Let's see if this is true by using Tinygrad. I'm going to start by importing the tensor class from Tinygrad. And now let's create a tensor with just one value. So this is a scalar tensor, and we have to say that it requires grad. Let's say that y equals x to the power of 4. Now the derivative of y, dy by dx, would be 4x to the power of 3. This is of course the power rule. So if we calculate this, we get 256. Currently the gradient property of both x and y is nothing. To calculate the gradient, we have to call the backward function on y. Now if we call numpy on the gradient of y, we see that it's 1. We always start with 1. But if we call numpy on the gradient of x, we see that it's 256. So now we are sure that the gradient is nothing but the derivative, a first order derivative. Of course, we were working with a very simple function. Usually we'll have to make use of the chain rule extensively. But while using Tinygrad, you don't have to worry about it. It all just works. And now we'll be writing a program where we do some gradient descent using Tinygrad. So start by importing tensor again. Let's also import numpy. We'll be plotting some data in this program, so import matplotlib as well. Let's define a harder function now. Let's say it's x squared plus x cubed minus 5x, and we calculate the cosine of all of this and then raise that to the power of 3, and we add 1.5 to it. This is a reasonably complicated function requiring the use of chain rule. I want to see what this function looks like, so let's create some data for it using the linspace function. The data will range from minus 1.5 to plus 1.5, say, and let's have 150 points. Let's cast this to float 32 because its data type is double by default, and that doesn't really work while using metal. And now we can just plot the data as the x-axis and the results of the function f as the y-axis. In the function, we need to make sure that the data is in the form of a tensor. So if it is not an instance of tensor, we make it an instance of tensor. And finally, let's show the plot. Let me run this. Cool. We have a descent function on which we can do some gradient descent. Let us now pick a point from which we are going to do the gradient descent. I'm going to choose minus 1.3. I'm going to quickly add this position to the plot as a green dot. So you have to say GO here. And let's run it again. Nice. So we are going to descend from that high point to the bottom of this curve, if possible. Back to the code. To be able to use a loss function, we need to know what the expected value is. Right now, let's just go with 0. If we approach 0, we are probably close to the global minimum of our function, right? And now we can create a for loop to start the gradient descent. Let's have 2000 iterations. To calculate the loss, we just calculate the negative mean squared error. And then to calculate the gradient, we call the backward function on loss. Now to descend based on this gradient, let's use one of the optimizers Tinygrad offers. I'm gonna use the Atom optimizer because it works really well. Create an instance of it here, and the only parameter we are working with is x, so pass that to it. And say that the learning rate is 0.001. And then in the loop, say atom.step. This way, we are going down that hill. I'm gonna print the loss here. Our loss, as you might have guessed, will never be 0 because our function never touches 0. So it's better if we break when the loss is, say, less than 0.3. We won't get the exact global minimum with this, but it will be close enough for our demonstration purposes. And here let's print the final value of x. Let's run the program again. Great, so we can see that the loss is decreasing. And finally, we see that the new x is minus 0.63. Let's add this position as well to our plot. But this time, let us make it a red dot. So say our O here. And we run it again. As you can see, we have actually descended to a point that's close to the global minimum. Let me now change x to a positive value and see how that goes. I'm going to set it to 0.04. And sure enough, we reach a different minimum. This is closer to a local minimum, but our gradient descent is working. Awesome. But how is this really working? Time to find out. So we are going to implement this whole thing from scratch now using just Python. So create a new file. Here we import just the cosine and sine functions from the math library. And we redefine our function using just Python now. So cosine of x squared plus x cubed minus 5x, and we cube that and add 1.5 to it. We can't use linspace because we can't use numpy, so we have to get a little creative. So create a range from minus 150 to plus 150 with a step of 2, and then divide each value by 100. So this should give us the same points approximately. To be sure about that, let's plot the function again. So import matplotlib. And here again, we have to use a for loop to pass each individual point to the function. Call plot.show, and then we run the new program. Great, so we got an identical plot. Let's pick a starting point for our gradient descent. Let's use minus 1.3 again. I want to add this point to the plot. So let's call the plot function again. And say GO here because this is a green point. Let's move the show function to the end of the program and let's run it again. Great, so we can see the green point. It is now time to calculate the gradient or the derivative of our function. So create a new function for that called derivative. Here we have to apply the chain rule. So first, let's apply the power rule to the cube of the cosine. So this will be 3 star cosine of x squared plus x cubed minus 5x raised to the power of 2. This whole expression is now multiplied with the negative sign of x squared plus x cubed minus 5x. And now we are finally working on the inner expression. So we have 2x plus 3 star x squared minus 5. Just applying the power rule to each term. The 1.5 constant is reduced to 0, so you can ignore that. This looks quite complex, isn't it? So we should appreciate how Tinygrad and other ML frameworks make our lives easier. Now that we can calculate the derivative, gradient descent is quite simple. Create a for loop with 2000 iterations again. Here we first calculate the gradient. And then we subtract it from x. But before we do that, we have to multiply it with a learning rate. Let's say it's 0.01. Actually, let's make the learning rate a variable. Okay, that's the gradient descent. We can now print the final value of x. We don't have a fancy optimizer, so it's very likely that we are going to descend only to a local minimum here. And then let's plot the new position of x. So we can just copy and paste this line. Just change GO to RO because this is going to be a red dot. And then call the show function of the plot. So if we run it, we can see that we have descended to a local minimum only. That's okay. I'm just going to change the starting x to a different value, say minus 0.84, and this should get us to the global minimum. So gradient descent is working. Thank you for watching. Please like and subscribe. Bye.